Okay, so let's talk about electromotive force here. This is from section 20.4, cell EMF under standard conditions. And what you have to realize here is this is basically the same thing that we've been talking about all year. Chemical reactions tend to happen spontaneously when they go from a state of higher potential energy to a state of lower potential energy. Just like a waterfall. Okay, the water falls down, obviously. Let me change my color here. Water falls down because it's going from an area of higher potential energy to an area of lower potential energy. In the same way, if you put two chemicals together that can perform a redox reaction, and there's an allowed flow of electrons between them, then the electrons are naturally going to flow from the anode to the cathode. Okay. Now there's a reason for that. Okay. The reason that one side is the anode and one side is the cathode has to do with how willing a particular element or compound is to lose electrons or gain electrons. Okay. If you put the anode and the cathode together, the anode is the one. Is the chemical species that is more willing to give up electrons, basically. It has a higher tendency to give up electrons. The species at the cathode is going to have a higher tendency to gain electrons. Alright? So this flow of electrons will only happen in one direction when you put two things together. They'll go from the anode to the cathode, from the one that's has a higher tendency to get oxidized to the one that has a higher tendency to get reduced. Okay? That's another way of saying that. That difference in potential is called the electromotive force, also called cell potential, also called cell voltage. Okay, you're going to hear me refer to it as all of those things. Those are all basically the same. Cell potential is measured in volts. A volt is 1 joule per coulomb. So this, because it's a ratio, it's kind of like density. Density equals mass over volume, right? That's an intrinsic property. It doesn't matter how much of it you have. That's, it's just an intrinsic property there, okay? So the amount of the substance is not entirely relevant here. Now I'm going to say something in the next couple of sections that seems to contradict that, but when we get to it, I'll explain why it doesn't. But it's an intrinsic property. Okay. So what has been done here is you've got, and this used to be something that you were given on the AP exam. You're not going to be anymore, which is actually kind of good news for you, I think, because they used to just give you this chart at the beginning of the test, and they wouldn't tell you in which problems you would need to use it. Now what they've said they're going to do is if you need the reduction potentials, they'll just give them to you in the problem. So that's easier because then you can just, you'll know when you need to use it, basically. But what this is, basically hydrogen has been made the reference point. Okay, so for H plus to be reduced to H2, is defined as 0 volts. Okay, now that's not the case. It doesn't mean that there's no potential difference between those two cells. So there is a voltage there, but they're going to define it as 0 because it comes in handy for the rest of these. Okay, so you define that cell as 0. Then what you can do is you can basically set up and this is a standard hydrogen electrode where you've got the H plus being reduced to H2. Okay? But what you can do with this is you can basically set up any other cells using hydrogen because we've defined that as 0. So let's say you set up another one here where you've got your platinum. I guess it has to be in the water. Okay, and then you've got your H plus running around in here, and then you've got some H2 gas on the outside of that, so all of that's in the one cell. And then you connect it to, say, I don't know, a copper cell. Maybe copper's a bad example. Let's do zinc. Okay, so you've got your electrode, you've got your zinc 2+, and your electrode here is made of zinc. Okay, so you've got your solid zinc and zinc 2+. These are connected with a wire like we talked about with voltaic cells in the last section. Basically, you can see which direction the electrons flow here, and you can use a voltmeter right here to measure the voltage. And if you set hydrogen as just the standard 0, then whatever voltage you get here, you can assign that number as a standard potential for zinc. So you come back over here, notice zinc is a negative 0.76. Okay, so what that tells me about zinc is that a negative voltage basically tells me that the zinc is going to have the tendency to get oxidized. So the electrons are flowing away from it towards the hydrogen. Okay, so the H plus is going to get reduced in that case and change into H2. And the zinc is going to change into zinc 2+ and go into the solution. Okay, so what that tells me, if I look back at this because this is a chart for reduction potentials, it tells me that zinc has a lower potential for reduction than hydrogen does. Okay, so in other words, you put hydrogen and zinc together, the H plus is going to be what gets reduced, not the zinc, not the Zn2+. Okay, so it basically just gives me a way to compare these things to one another. This is the activity series flipped backwards, because the activity series, the more active metals are the ones that more readily give up their electrons. So those are the ones that are more easily oxidized. Okay, this is the reduction potential chart. The higher it is on the chart, the more easily it is reduced. Okay, so you've got your fluorine up here at the top, plus 2.87. So that means that when you put fluorine with hydrogen, the standard hydrogen electrode, the fluorine has a much higher potential to be reduced. So that means that it's going to take the electrons away from the hydrogen. So the electrons are going to flow towards the fluorine, and it's going to get reduced. It's going to be the cathode, is the other way to say that. And it means that the voltage reading that you would get out of that reaction is a positive 2.87. Okay, so it's a very high voltage reading because there's a big difference between their reduction potentials. So by the analogy, this is a very high waterfall where the water, by the time it hits the bottom, is falling very fast because there's a big difference in potential energy there. Okay? Well, actually, let me go back to this for a second. At the bottom of this list, you've got lithium. Okay? Lithium does not like to be reduced. It likes to be oxidized, which should make sense because it's far to the left on the periodic table, right? It's going to tend to lose electrons, not gain them. So it shouldn't surprise us that it's at the bottom of this list. Lithium is actually towards the top of the activity series. So again, that shouldn't surprise us at all because it's going to tend to give away electrons, so it doesn't want to gain them, which is what reduction is. It's gaining electrons. Okay. You can calculate these standard cell potentials using this formula right here. Okay, and that's basically using this chart. Okay, so if you're given reduction potentials, standard reduction potentials, or a chart of standard reduction potentials, then you can figure out the voltage, the hypothetical voltage that any cell should have. Now standard, we need to kind of define what standard means. It means that the concentrations of your cells, okay, so whatever cells you're creating here, would be 1 molar concentrations. Okay, so the zinc 2+ is a 1 molar concentration to start out with. The H+ concentration is a 1 molar to start out with. And then any gases you have in there, like the H2, would be at 1 atmosphere of pressure. Okay, this is also taking place at 25 degrees Celsius, so that's what standard means. So basically, if you're under standard conditions and you hook these two cells up, what would the voltage reading be? You can figure that out. Okay. So here's an example. If you've got zinc and copper hooked up together, then you basically just look back at the at the potentials, okay? Now, notice which direction the electrons are going. They're going from the zinc to the copper. Now, we could have predicted this by looking at this chart, right? If you see where zinc is, zinc's right here, copper's up here. Copper's higher on the reduction potential chart, so the electrons are going to flow to the copper. Okay, copper's going to be the one that gets reduced. So that should make sense. So our anode is zinc, our cathode is copper. Okay, because again, red cat, right? Reduction happens at the cathode, and oxidation happens at the anode. Okay? Alright, so then here's your overall reaction for this. Now if you want to figure out the voltage, if you don't have a voltmeter connected to this and you want to figure out what your hypothetical voltage should be, and again, these are 1 molar concentrations of solutions here to start out with. They're not gonna be that way at the end, but that's how they're gonna start. Then you just take the reduction potential of the cathode minus the reduction potential of the anode. Okay? So again, cathode is copper because it's the one that's gaining the electrons. So if we look at the reduction potential on the chart, it's plus 0.34. Okay, so you plug that in, minus the reduction potential for the anode. Well, if you look at zinc, which is the anode, it's a negative 0.76. Okay, so you plug that into the equation. Minus a negative is going to end up being positive here. Okay, so you end up adding those two together and you get a positive 1.10 volts. Okay, for any reaction that's happening spontaneously, you're going to have a positive voltage. So if you figure this thing out and you get a negative voltage, it means you probably didn't identify the anode and the cathode correctly. Okay, you probably picked the wrong things for the anode and the cathode, and you'll need to flip them. Alright, take a look at an example here. It says, using the standard reduction potentials listed in table 20.1, calculate the standard EMF for the voltaic cell based on this reaction. Okay, so we've got two half reactions happening here. You've got the Cr2O7 2 minus 2Cr3 plus. Okay, now that's not balanced, obviously. That's not a balanced half reaction. That's just the skeleton half reaction, but we can use that for now. And then you've got your 6I minus going to 3I2. Okay, now we can look back at our reduction potential chart here, and we actually have both of those. Okay, so if you look at it, again, my first reaction here is Cr2O7 2 minus going to Cr3 plus. So if I look on the chart, that one is right here. Okay, so there's that reaction, and that has a potential of plus 1.33. Okay, the other reaction that's happening is iodine I minus going to I2. Okay, now that one's written backwards here, okay, but here it is. Okay, so between those two, the reduction that's most likely to happen, the one that's higher on the chart, is the Cr2O7 2 minus, okay, the one with the plus 1.33. So that means that's going to be our reduction reaction. The oxidation is going to be the one down below. Okay, now you could look at the overall reaction and you could figure that out anyway, because I minus going to I2 is an oxidation, right? And chromium, I think, starts out as a 7 plus oxidation state on the left side, and it becomes a 3 plus, so that's a reduction. Okay, so both of those ways kind of show us the same thing. So the important thing here, this one's undergoing the reduction, so it's the cathode. This one is going to be the anode because it's undergoing the oxidation. Right, and we need to know that because we're going to use the formula here to calculate the E0 for this cell, okay, which is the standard EMF. Alright, so what we do here is we take the reduction potential of the cathode, which, again, coming back to this chart, is plus 1.33. Minus the reduction potential of the anode, which is plus 0.54. And those are both volts. I didn't label it. Okay? But once you figure that out, you're going to get a voltage of 0.79. That's a positive. I didn't label it with a positive, but it's, I didn't put a negative, so that's assumed. Okay. Now this is important, okay? I know there's some coefficients there, and I know you're going to think, well, do I multiply this thing by 3 because there's coefficients, or by 2 because there's coefficients? The answer is no, because remember, this is not based on, it's an intrinsic property. In other words, it's not based on the amount of moles that you have here, okay? So the voltage is just what it is, okay? You just look at the chart and it will tell you, okay? You just use the reduction potentials on the chart. So that's how you calculate this every time. Regardless of what the coefficients are in the balanced chemical equation, you don't have to worry about those right now, okay? Alright, one more practice problem here. By the way, just a note here, this is a positive voltage, so that means that we did it correctly. Okay, if you come up with the answer and it's a negative voltage, you probably flipped the cathode and the anode. Alright, now on this one we did it right, so I'm going to cross out that arrow. But if you get a negative voltage, that's probably what you did. Okay, next one, voltaic cell based on the following two standard half reactions. It says, by using the data in Appendix E, which is basically what's on the standard reduction potential chart, determine the half reactions that occur at the cathode and the anode and the standard cell potential. Alright, so both of these half reactions are written as reductions here. If you notice, the CD2 plus is gaining electrons and becoming CD, the SN2 plus also gaining electrons and becoming SN. Alright, so what we have to do is come back over here to the reduction potential chart, find both of those things. Nope, take it back. They're not on there. That's why it says to use Appendix E, because I guess that's a more complete list. Okay, so I'll just give you those values because that's what's going to happen on the AP exam. So the E0 reduction value for the CD2 plus is negative 0.403 volts. Okay, and then the reduction potential value for the 10 is negative 0.136. Okay, so they're both negative, but the one that is the least negative, in other words, the one that's the bigger value, is going to be the 10. Okay, so our 10 is the one that's getting reduced here, which means by default the cadmium is the one that's getting oxidized. Okay, so the one that's getting reduced is going to be our cathode, and the one that's getting oxidized is going to be our anode. Okay, now that we know our anode and cathode, we've answered part A, so now we can answer part B by just doing basically the same thing that we did in the last problem. So the E cell there is going to be the reduction potential of the cathode minus the reduction potential of the anode. So cathode is negative 0.136 volts minus a negative 0.403 volts, which that's the reduction potential of the anode. Okay, and notice we're minusing a negative here, so these are going to become positive values, and that's going to give us a positive number. It's going to give us 0.267. Okay, and again, we did it right because we got a positive voltage out of it. And so that means that the electrons are going to be flowing, if we set these two up, then the electrons would be flowing from the 10 to the cadmium. Okay, and let me just sort of draw this out, because again, I think it's helpful. So you've got our two beakers, right? Got your, on one side you've got your, and you can draw this however you want. I think the convention is usually to put the anode on the left side, cathode on the right. But I don't know if that matters all that much. But there's our 10, and then in the solution we have SN2+. Okay, and then over here we've got our cadmium metal, and then our CD2+. We've got these connected with wires, and we've got our salt bridge here, and then we've got a voltmeter in the middle. Okay, so what I'm saying here is, oh, see, I said it right, but then I wrote it backwards. But again, I don't think it matters all that much. The direction of the electron flow here is going to be from the cadmium, from the anode, to the cathode. Alright? So that's your flow of electrons there. And that's basically what we're saying when we say anode and cathode. So I just want you to understand the picture that goes along with it. Okay? Alright, I think that's pretty much it for this section. I'll just mention, and I mentioned this several times on the reading guide for this, but you don't have to worry about oxidizing and reducing agents. The AP exam specifically said in the curriculum that they're not going to be testing on that, so you don't have to worry about that part of the section. Alright, I guess we'll see you in class.